Hello students, in the present video session, we'll discuss about integer division. An n-bit positive divisor is loaded into register M. An n-bit positive dividend is loaded into register Q at the start of the operation. So that means initially we can load divisor into register M and dividend Q into register Q. And we can take one more register A and we can initialize that register with zeros. After division operation, the n-bit quotient is in register Q and the remainder is in register A. So this is a circuit arrangement for binary division. So each time we have to perform a shift operation, shift left by one binary position, and we have to subtract M from A. So that is the control sequencer, it will perform add bar subtraction operation, and after that we have to check the sign of A. If the sign of A is 0, we can set Q0 is equal to 1. If the sign of A is 1, and we can set Q0 is equal to 0. And we have to repeat n times the same steps. So first we'll take non-restoring division. So the basic procedures are given as below. Step 1, do the following n times. If the sign of K is 0, shift A and Q left 1 bit position and subtract M from A. Otherwise, shift A and Q left and add M to A. Now, if the sign of A is 0, set Q0 is equal to 1. Otherwise, Q0 will be set to 0. If the sign of A is 1, add M to A. That means restore operation. So now, we'll take one simple problem and we can check how we can perform division operation. So first I'll take the divisor M. Divisor M is equal to 0, 0, 0, 1, 1 and dividend Q equal to 1, 0, 0, 0. So first I'll initialize A and Q. I'll take A and Q. So I'll take register A and I'll take register Q. So first I'll write Q as it is and I'll initialize A with all zeros, and while considering the number of zeros in register A, always have to add one extra bit than M. So the first step is, so we have to shift left A and Q by one binary position. So this vacant location I'll keep as it is. So this 0 will come to the previous location, 0 will come to the previous location, this 0 will come to the previous location, and this 1 will come to this location. 1, 0, 0, 0, 0. So now after that we have to perform A minus M. I have to perform A minus M. So A minus M, which is equivalent to A plus 2's complement of M. So for that I'll take M as it is 0, 0, 0, 1, 1. So I'll complement all the bits 0, 0, 1, 1, 1 and I'll add 1. So I'll get 1, 0, 1, 1, 1. So this is have shifted left here, shift left. So now we are performing A minus M. So I'll write A as it is 0, 0, 0, 0, 1 plus 2's complement of M. So that is 1, 1, 1, 0, 1. So now add 1 plus 1 is 0, 1, 1, 1, 1. So now check the sign bit. Check the sign bit. If the sign bit, if it is 1, set Q0 is equal to 0 and restore. Restore. So while restoring, we know that A minus M, restore means I have to add plus M. A minus M we already computed, have to perform A plus M. So that means directly I can write this value before performing A minus M. That means we restore the value of A. So restore in the sense 0, 0, 0, 0, 1, and I will write Q as it is 1, 0, 0, 0. So now I can say that we completed the first cycle. We completed the first cycle. So next I'll copy the value from the first cycle. After restoring, we got the value of A as, this is A, that is 0, 0, 0, 0, 1, and Q is 0, 0, 0, and within the box 0. So now we have to continue with the second cycle. So once again shift left by one binary position. So the last position will be empty. So this 0 will come to the previous location, and this 0 will come to the previous location, this 0 will come to the previous location, this 0 will come to this location. So that is 0, 1, 0, 0 and 0. So this is nothing but shift operation, shift left. After shift operation, what we have to do? Subtract M from A. That means I have to perform A plus 2's complement of M. So I will write A as it is, that is 0, 0, 0, 1, 0, and I will write Q as it is 0 blank. And now we know that 2's complement of M is, we already computed, that is 1, 1, 1, 0, 1. So we will get 1, 1, 1, 1, 1. So now check Q0 bit. Since it is 1, set sign of A is 1, set Q0 is equal to 0, and we have to restore. Restore in the sense initial value of A I have to write before performing A minus M. So now, so this is a new value 0, 0, 0, 0 after second cycle. So now I can say that we completed second cycle. So we'll proceed with the third cycle. For that I'll copy the value. I'll copy the value of A and Q. So I'll write this is A, this is nothing but Q. So we got 0, 0, 0 and 0, and this was 0, 0, 0, 1, 0. So now once again have to shift it left. So the last position will be empty. 0, 0, 0. This 0 will come to the previous location. 0, 0, 1, 0, 0. So now subtract M from A. So this is shift left we perform. Now subtract M from A. That means I'll write A as it is, and I'll add 2's complement of M, that is 1, 0, 1, 1, 1. So that is 1, 0, 0, 0, 0, and carry we can neglect. So now this value I will write as it is 0, 0 and blank. So now check the sign bit. Since it is 0, I can set Q0 as 1. No need to restore. No need to restore. So now I can say that this completes third cycle. Third cycle. So once again we have to proceed with the next cycle. For that I will copy A and Q. So A value is 0, 0, 0, 0, 1 and Q was 0, 0, 0 and 1. So now this is A, this is Q. So shift it left by one binary position, blank, 1, 0, 0, and this 0 will come to the previous location. So we'll get 0, 1, 0, 0, 0. So now we have to perform A minus M. That means A plus 2's complement of M. 2's complement of M is 1, 0, 1, 1, 1, 1, 1, 1, 1, 1 you'll get. So check the sign bit of A. Since it is 1, so this one I will copy it once again, 0, 0, 1 and blank. Since it is 1, set as 0, and since it is 1, we have to restore. Restore in the sense I'll get 0, 0, 0, 1, 0 and 0, 0, 1, 0. So we know that always A carries the remainder R and Q carries the quotient Q. Quotient. So I can say that we performed the operation 8 by 3 and we have to get remainder as quotient as 2 and remainder as 2. So we are getting the correct answer, remainder as 2 in binary and quotient is equal to 2 in binary. So this is how we can perform the division operation using restoring binary division. So we'll take one more problem. Perform division operation using restoring division where M is equal to plus 4 and Q is equal to plus 25. So first I'll initialize A with zeros. I'll take 6 zeros and I'll write Q as it is. Q is given in the problem, that is 25, 0, 0, 1. So first step is we have to shift left by one binary position. So I'll get the last column will be empty, 1, 0, 0, 1 and this one will come to the previous location, 1 followed by zeros. So now we have to consider A minus M, that means A plus 2's complement of M. So for that I'll write M as it is. So the value of M is 4, that is 0, 0, 1, 0, 0. So I'll take 1's complement of this 0, 1, 1 and plus 1 gives the 2's complement of that 0, 0, 1, 1, 1. So I'll write as it is. So that is 0, 0, 1, 1, 1. So I have to add this 1, 0, 1, 1 1. I'll write Q as it is 1 0 0 1 blank. So now I have to check the sign of A. Since sign of A is 1, set Q naught is equal to 0 and we have to restore. Restore in the sense I'll get the original value of A before performing A minus M 0 0 0 0 1. So I can say that this completes the first cycle. Completes the first cycle. So now I'll write A as it is and I'll write Q as it is 1 0. So now I'll start performing the operation. So that is, first I have to shift it left by one binary position. This 0 will come to the previous location and the last location will be empty 1 0 0. This 1 will come to the previous location. So 1 1 followed by zeros. Followed by zeros. So now I have to perform A minus M. That means I'll add 2's complement of M 0 0 1 1 1. So I'll add, I'll get 1 1 1 1 1. So I'll write Q as it is and 0. So now I'll check the sign bit. Sign bit is 1. So I'll set Q naught is equal to 0 and I'll perform restore. Restore in the sense 0 0 0 1 1. I'll write 0 0 1 0 and 0. So this completes the second cycle. So now I'll copy as it is, that is 0 0 0 1 1 0 0 1 and 0. So now shift it left by one binary position. Last column will be empty 0 1 0. This 0 will come to the previous location 0 1 1 0 0. So now I have to perform A minus M. That means A plus 2's complement of M 0 0 1 1 1. So 0 1 0 0 0 1. So now check the sign of A. Since it is 0, set Q naught is equal to 1. No need to restore. No restore. So that means I can write as it is 0 0 0 1 0 0 1 0 and 1. So now this is 0. I have done a mistake here. This is 0. This is also 0. This is also 0. So now once again shift it left by one binary position. So the last column will be blank 1 0 0 and this 0 will come to previous location 0 0 1 0 0. So next we have to perform A minus M. That means A plus 2's complement of M. So I'll 0 0 1 1 1. So I'll get 0 0 0 0 0 and 1. So check the sign bit of A. So since it is 0, set Q naught is equal to 1, no need to restore, no need to restore. So that means the value of AV is 0, 0, 0, 0, 0 itself, and Q is 0, 0, 1 and 1. So now once again we have to perform shift operation. Shift it left by one binary position, blank 1, 1, 0 and 0. So now this is 1, 0, 0, 0, 0. So perform A minus M, that means we have to add 2's complement of M, 1, 1. So we'll get 1, 0, 1, 1, 1, 1. So since it is 1, set Q naught as 0 and restore. Restore in the sense, so I'll get 0, 0, 0, 0, 1. So this is nothing but remainder R, and quotient we got it as 0, 0, 1, 1, 0, that is equal to 6. So we perform the operation 25 by 4 by 4. So we have to get remainder as 1 and quotient as 6.